All right, welcome everyone to this lesson on the reduction potential table and the spontaneity of reaction. Before we begin, just stop and print out the sheet that you'll find underneath. It's called the standard reduction potentials. It looks like that. You make sure you just pause this video right now and go ahead and print it, and we'll come back. All right, so what we're going to be looking at is why some redox reactions are spontaneous and why some are not. Now, what do we mean by spontaneous? It means that there's no kind of external force applied. So in this case, when we see is we have a strip of magnesium put into a beaker of Ag plus ions. So how do we get those Ag plus ions? It could be something like AgNO3 aqueous, so that when we put it into solution, we'll get Ag plus ions, and we'll also get some nitrate ions. And so in this case, when we put these two together, what we see is that the Ag and the Mg react. What's actually happening is the Ag is coming out of solution, and it's forming on top of the Mg. So what's actually happening is we have a redox reaction occurring. Mg solid, the strip of Mg, is actually going into Mg2 plus 2 electrons, and the silver is going from Ag plus, in this case, in the aqueous form, it's gaining an electron and is becoming Ag solid metal. Now, obviously, this is not balanced because we see that we have one electron lost and two electrons lost, one electron gained. So we'd have to use some coefficients to multiply the electrons. So that means that the electrons being gained and the electrons being lost are the same. Now, if you remember, when something is reduced, that means it's gaining electrons, and when something is oxidized, it's losing electrons. So in this case, Ag plus is being reduced and Mg is being oxidized. Okay, so we can see that this is a reaction, spontaneous, it happens by itself. But in the case of here, putting lead in magnesium 2 plus, for example, we see that there is no reaction that happened. And this has to deal with how readily something wants to be reduced or how readily something wants to be oxidized. So we've done a bunch of experiments in the past, and we've kind of grouped things into strong reducing agents, aka they want to be oxidized, and strong oxidizing agents, aka they are reduced, so they gain electrons. And we kind of put this table together to create this standard reduction potential table. Now, the way that this works is that you have these values here for the standard reduction potential. Now, what that means is how easily it wants to, or how favorably it is when it gets reduced. So something with a positive number in terms of the potential means that it really wants to get reduced. While something with a negative number means that this species over here, in this case Li+, does not want to get reduced because it has a very negative value. Versus F2+, it really does want to get reduced, it really does want to gain electrons because it has a positive standard reduction potential. That's the key that we're looking at, reduction potential. So it's the ability to be reduced. Okay, and that's what we see if we split this table down, the arrows, all of these species on the left-hand side, they're all gaining electrons. They're all being reduced to produce this. Okay. And we'll talk about the relationship of what happens if we flip this reaction. So if we flip this reaction, for example, to go the other way, what we'll see is that this value also flips in terms of its sign, Hess's law. So our standard reduction potentials, how are these kind of determined? Well, they show a difference in the voltage between the two electrodes. So in the two electrodes, we mean the cathode and we mean the anode. And we'll talk more about that when we get to galvanic cells. But in this diagram over here, what we see is we have tin, Sn, and we have Cu2+. Now tin, what we're seeing in this case, is that tin is actually losing its electrons. Okay, it's losing. So that means that tin is being oxidized. Okay. Oxidize. You need to learn how to spell there. It's oxidized. So if it's oxidized, that also means that it is the reducing agent. Okay? It's reducing the Cu2+, which is gaining the electrons. So as Sn turns into Sn2 plus 2 electrons, those 2 electrons are being picked up by copper, where Cu2 plus is picking up those 2 electrons and turning into Cu metal. And so what's happening in this kind of diagram, what's trying to describe is that there's potential energy here, lower potential energy. So this difference in potential energy is what is being calculated here. And that difference in potential is how we get our standard reduction potential. So once again, this table shows the species desired to be reduced. And again, the species that we're talking about is the species that is on the left-hand side. So when we look at this value here, this value is associated with the Cu2 plus because it's on the left side of the arrow. Okay, it's the side that's gaining the electrons. So this is the reduction potential, therefore. If we look at lithium, for example, again, it has a very negative value, which means that Li plus does not want to be reduced. A negative value shows that it does not want to be reduced. Okay? It wants to be oxidized, and therefore it is a strong reducing agent. Okay? So as we go from here, the desire for Cu2 plus to be reduced is much greater than the desire for Li plus to be reduced. And because here they want to be reduced, what that means is that as you go up this table, as you go this way here, what you're getting strong oxidizing agents. The opposite is true here. As you go down this way, your desire to be oxidized is increasing. Okay? And so as you go down, you're going to have strong reducing agents. Okay? So again, lithium has a very negative value, which means that it does not want to be reduced. And as you can see that these values are kind of relative to this 0, 0, 0 term, and we'll talk about that in a few moments. So just the flip side, the more positive a value is in the standard reduction potential, the more it wants to be reduced. Okay, so in this case here, again, if we look at Sn and Li, Li has a negative value, Sn has a positive value, so that means it wants to be reduced. But let's compare these two, for example. Let's look at barium 2 plus and lithium 1 plus. What's happening is that the magnitude is also important, because here we have a negative 3.05, here we have a negative 2.9, so both of them are negative values, but if one of these had to be reduced, it would be this one here, because it puts up, in a sense, less of a fight than the lithium, because it has this less negative value. So again, the more negative, the more it does not want to be reduced. Okay, so let's look at this. So we know that lithium 1 plus does not want to be reduced. It has a really no negative reduction potential. But what if we do the opposite? What if we oxidize Li? We oxidize the opposite side of this. Does that want to, would that be a favorable reaction? So if we oxidize, that means we're taking a solid and we're causing it, to lose its electrons. Okay, Li is going to form a 1 plus ion because it's in group number 1, so it's going to lose 1 electron. So will this be favorable? Well, like we did in Hess's law, we saw in thermochemistry, whenever we flip the equation, we also flip the sign convention. So in this case, this will be positive 3.05. And again, this is in volts. Now, but what we've done is, because we now have an oxidation reaction, this is our standard oxidation potential. Okay, so what this means, just like the standard reduction, when we had a standard reduction potential that was positive, it means that it wanted to be reduced. Because we now have an oxidation reaction, we have converted this into a standard oxidation potential, and the more positive it is, the more it wants to be oxidized. Okay. The more negative it is, the less it wants to be oxidized. Okay, so the same kind of thing. Once you flip the equation, you flip the sign convention, and so something that initially does not want to be reduced because it has a negative value, if you flip it, well, now it would have a positive value, and it would want to be oxidized. Okay. So in this case, we have our summary. A few other things. You'll notice that it says standard. What standard means is that we measure all of these potentials at 298 Kelvin, which is the same as 25 degrees Celsius. We also, if we're dealing with gases, all the pressures are equal to 1 atmosphere. And if we're looking at solutions, all the solutions are 1 molar solutions. The other thing is that you can see here when we're talking about the 0, 0, 0, this is called a standard hydrogen electrode. And basically it's hydrogen, there's a platinum electrode, And so all of these values, top and bottom, are all relative to this. So oxygen, this standard hydrogen electrode, is just an arbitrary number. It's given 0, and everything else is just is based off of that. So what we're trying to figure out with this table and to use it is to see if a reaction is going to be spontaneous. So something that's spontaneous means that there's no external force required to keep it going. Okay, so nothing is needed for it to go. It just happens by itself. Non-spontaneous means that it will need something to like a continuous external stimuli to keep going. It won't happen by itself. So to predict spontaneity, we can do this in 2 ways. The easiest way is using this diagonal rule to predict it, but if we really want to confirm it and kind of check our predictions, we'll use our standard reduction potentials to calculate the electromotive force. So the diagonal rule is pretty simple. Based on our standard reduction potential, we'll have a whole bunch of lists of things that are being reduced. So it's something, let's say for example, A plus gains an electron to produce a solid. And there you go. And we have a whole list of these different reduction reactions. If we find, and we're trying to predict whether something will react with something else, we just find it on the list. So if our oxidizing agent is higher than our reducing agent, you're going to have a spontaneous reaction. However, if it's the opposite, your oxidizing agent is lower than your reducing agent on the table, you're going to have a non-spontaneous reaction. Okay, we're not going to have a reaction. It's just not going to happen. So let's take a look. Here's a little example. Predict whether the following reactions will be spontaneous. So this is when you need to use your list. I have a little bit of a list here on the edge, just to give us an idea. It's a very annotated list. But the first thing is that we need to figure out what our reactions are, what things are being reacted. So here we actually have a part of a molecular formula. Now if we were to draw out the rest of the formula, we know that this is a single displacement reaction. So Ag would form with NO3, aqueous, plus we would have zinc metal, solid. Now because NO3 is found on both sides, it's our spectator ion. So basically what we we'll have Ag plus, to balance this, we'd have that there. So we'd have 2 Ag plus, 2 Ag just by itself because it's metal by itself, plus zinc 2 plus, aqueous, and that reacts to form 2 Ag plus aqueous plus zinc metal. Okay, so what are our reactants? Well, our reactants are Ag and zinc 2 plus. So let's go ahead and find those on our standard reduction potential table. So if we look at the table on our right over here, let me just erase that there. So if we look at our table here, let's try to find out where our 2 reactants are. Here we see that we have Ag, and here we see that we have Zn2 plus. So what we can see is that our Ag is higher than our zinc 2 plus. So what our prediction is that this is going to be non-spontaneous. Now that's just a prediction. I'll show you later on how to actually figure that out. So here's our next little practice here. Predict whether the following reactions will be spontaneous. Here we have lithium metal reacting with copper 2 sulfate. So take a few moments, use your standard reduction potential table, and try to predict if this is going to be spontaneous or not, and we'll come back in a second. So just go ahead and pause the video now. Okay, so welcome back. What we have is I've just written out the rest of the molecular equation and got rid of our spectator ions, which was the SO4 on both sides there. So in this case, what we're trying to look at, we're trying to find out where our reactants are. So our reactants, we have lithium right here, and we have copper 2 plus, which is right over there. And our copper 2 plus, which is being reduced, our oxidizing agent, is higher than our reducing agent, the Li. And so because of this, this is going to be a spontaneous reaction. Okay? So in trying to figure this out, what we do is we list all our present entities. So we turn the molecular equation into the net ionic equation. We classify as whether they're going to be oxidizing or reducing. And so again, if they're gaining electrons, if they're going from a plus to a solid, an aqueous to a solid, usually that they're gaining electrons. And if they're losing, they're going from a solid to an aqueous for most cases that we're going to be dealing with. and so they're going to be losing electrons. And so we find it on our table, and we're going to predict our spontaneity using our our diagonal rule, and then we can write our half reactions and multipliers to bounce off the electrons. So, using the standard reduction potential tables, predict if this reaction will be spontaneous or not. So a strip of tin is placed into a solution of silver nitrate. So go ahead, try to write out your full equation, turn it into a net ionic, figure out which one's being oxidized, which one's being reduced, find those things on the table, write out your half reactions, balance off for the electrons, and write out your full reaction, and let's see what we can do. So go ahead, pause this, spend a couple of minutes on it, and we'll come back with the answer. All right, go ahead and pause the video. All right, welcome back. What we have here is we have the complete molecular formula between tin and silver nitrate. So what we saw is that we created this total ionic equation, or net ionic equation. We have tin plus 2 Ag positives, Sn2 plus, and 2 Ag. And I was able to create this whole reaction here by knowing that my Sn and my Ag did create a spontaneous reaction, and from that I was able to figure out that my Sn was being oxidized. It was losing 2 electrons to get to the positive, and my Ag plus was being reduced. It was gaining electrons to be there, and so I knew that that was my reduction agent and that was my oxidizing agent. All right, so one way that we can confirm is using something called electromotive force. And so we're actually going to be using the voltages on our standard reduction potential to calculate this. And we calculate something called E cell. And so that's the difference in potential difference between the two electrodes and the two half reactions. So what we look at in this case is really what the overall sign is. And that will help us figure out whether it's going to be spontaneous or not. So a positive sign, so a positive voltage. So it doesn't really matter what the number is, but as long as we have a positive voltage, we're going to have a spontaneous reaction. And if we have a negative voltage, again, at this point, it doesn't really matter about the number, but if we have a negative voltage, that means that it's going to be a non-spontaneous reaction. So it wouldn't happen with any kind of, unless there was an external placed on it. So to calculate the E cell, what we want to do is figure out which species is being oxidized and which one is being reduced. Then we write our half reactions to reflect those processes. We use multipliers to balance the electrons, and we add them to get a final E cell reaction. And we calculate that by using this equation over here. So E cell is going to be the electron, the standard reduction potential for the reduction reaction, as well as the the potential for the oxidation reaction. Now, what you notice is that we have oxidation. So these are the values in the table are the standard reduction potentials. So to get this, we'll just have to take that value and flip the sign for the oxidation reaction. So let's do a little example here. The question is, can Pb2 plus oxidize aluminum? All right. So in this case, the first thing that we need to realize is what this little statement is saying. It means that aluminum is being oxidized. So in this case, let's first predict. So it says that Al is being oxidized and Pb2 plus is being reduced. All right, so if that's the case, then our kind of equation, let's just do some half reactions here and see what we get. So if Al is oxidized, that means it must be losing electrons. So it goes from a solid to an ion. Now, if you look at your periodic table, you remember that Al goes from Al and 3 to 3 plus because it loses 3 electrons, and that would be aqueous plus 3 electrons. So that would be what we're saying, because we're saying that Al is being oxidized, it is losing electrons. Now, if Al is oxidized, that means Pb has to be reduced, so Pb2 plus is going to be gaining electrons. Well, we have a charge of 2 plus here. It wants to neutralize that charge, so it's going to gain 2 electrons to form Pb solid. Okay, so let's take a look at this. In this case, if we kind of join our reactions together just briefly, what we'll notice is that we would get, if we kind of split the sides here, Al plus Pb2 plus. Don't worry about the electrons right now, but if we have Al and Pb2 plus, so let's find those things on the table here. We have Pb2 plus and we have Al. Well, look at that. Based on our diagonal rule, this should be a spontaneous reaction. This should be a spontaneous reaction. So let's go ahead and calculate this out. We already have our half reactions here. And so if we just go ahead, and just redo that there. We have our half reactions. So what we want to do is we want to figure out what the E cell values of these are. So in this case, our Pb2 plus 2 electrons, this equation right over here, is exactly the way that we see it right over here. And we see it the exact same way, so we don't have to change that voltage. We're just going to write it down. So our E of, in this case, we're gaining electrons, so that's going to be reduction. The E of reduction is negative 0.13 volts. Now, the Al version up here, it looks very similar to this equation here, except that it's reversed. We will go from Al solid to the Al3 plus 3 electrons. In this case, this is the reduction. So this is our oxidation reaction. We flipped this reaction around. And so because we do that, we have to also flip the sign convention. So in this case, when it was being reduced, it was a negative 1.66. It did not want to be reduced. But because it's now being oxidized, we flip that sign, so we get positive 1.66 volts. So that is our our oxidation potential and our reduction potential. Now, when we look at these two equations, we have to join them, but we have to make sure that the electrons being lost and gained are the same. So the common factor between the 3 and the 2 is 6. So what I'm going to do to this equation is I'm going to multiply it by 2, and I'm going to do this one, I'm going to multiply it by 3. Now, there's a very, very important thing to note from this example, is that even though we are multiplying the number of electrons and consequently the number of atoms and ions, we never ever multiply the potential difference. Potential difference is an intrinsic factor, and so therefore it doesn't really get multiplied, or not doesn't really, but it doesn't get multiplied by any kind of coefficients. So what we're going to get here is we're going to get 2 ALs, 2 AL solids, plus we're going to get 3 Pb2 pluses, and we're going to get 6 electrons on this side, and that's going to give us 2 Al 3 pluses aqueous. Put a little aqueous on this side, plus 3 Pb solids, and again 6 electrons. So what we can do is, because we have 6 electrons on both sides, we can cancel those out and write our final equation here: 2 Al solid plus 3 Pb2 plus aqueous, giving us 2 Al3 plus aqueous plus 3 Pb solid. Now we're still not done. That's our total, our net ionic equation. We need to figure out if this is spontaneous or not. So to find E cell, we just add the two. And so here we have plus 1.66, and we subtract 0.13 volts. So our E cell is positive 1.53 volts. Now again, the number right now doesn't really matter, but what does matter is our sign. In this case, we have a positive sign, so yes, this is spontaneous. Alrighty, so in this case example, what we have, the question is, can Pb or Pb2 plus can oxidize Cu? So it's giving you statements, asking you true or false. Alright, so again, what this means is that Cu is being oxidized. So Cu is going to be losing electrons. So Cu2 plus 2 electrons, and Pb2 plus is going to be gaining 2 electrons to create Pb. So in this case, if we look on the left sides of our arrows, we'll have Cu and Pb2 plus. So let's just find those on our little cutout here of our standard reduction potentials. Here we have Cu, and here we have Pb2 plus. And what we can see is it doesn't look very good right now, because based on our diagonal rule, it should not be spontaneous. So let's just write out our half reactions here, put the E cell, the reduction potential values with it, and see what we can get. So I'm just going to rewrite the equations here. Pb2 plus aqueous joins with 2 electrons to produce Pb solid, and your other reaction is Cu solid to give us Cu2 plus aqueous plus 2 electrons. Okie dokie. Just kind of for continuous sake, Pb is being reduced because it's gaining 2 electrons, and the Cu is being oxidized here. Okay. Now, our E cell values for this is our ER, it's our reduction potential. For Pb2 plus is going to be negative 0.13 volts, exactly as we see it over here, because our reaction has not changed. It's in the same format. Our Cu reaction has been flipped, so our oxidation potential is going to be not plus 34, but negative 0.34 volts. So again, in this case, we want to make sure that our electrons are balanced. Here we have 2 being gained and 2 being lost, so that's perfect. We don't really have to do anything there. We can just cross things out. And our final reaction will be Pb2 plus aqueous plus Cu solid, giving us Cu2 plus aqueous plus Pb solid. That's our final or net ionic equation. And our E cell, we just take our reduction potential plus our oxidation potential, and our final value is going to be negative 0.47 volts. So once again, the number doesn't really matter for us right now. It's all about the sign, and a negative sign means that it's going to be non-spontaneous. So this agrees with our original prediction using our diagonal rule. So the question again is saying true or false. Pb2 plus can oxidize Cu. Because we got an overall non-spontaneous reaction, we are going to say that this is false. Pb2 plus cannot oxidize Cu metal. All right, so here's your opportunity to practice. The question is, can zinc reduce Ni2 plus? So use your standard reduction potentials, pause the video, and we will come back to give you the answers. So go ahead and pause the video now. All right, so welcome back. Here we have our answers. So in this case, the nickel 2 plus is being reduced into nickel solid, and the zinc metal, is being oxidized into zinc 2 plus. So our final net ionic equation we have below it. Now again, because the zinc is being oxidized, we had to flip the sign of the reduction potential into an oxidation potential. So it becomes positive 0.76. So when we add these together, we get a total of 0.50 volts, and because it is positive, it is a spontaneous reaction. So yes, zinc can reduce nickel 2 plus. All right, that's the end for this lesson. Practice out on your sheets, and we'll see you in a bit.